Okay, we are going to do the problems for the worksheet for chapter 3. So the first problem, a cannon is set at an angle of elevation of theta equals 35 degrees. That is, angle of elevation means angle above horizontal, on a cliff that is 55.3 meters above the ocean. If a ship is sailing 1.575 kilometers away from the cliff, how fast must the cannonball exit the cannon to hit the ship? Also, how long will it be between when the cannon fires and the cannonball hits the ship? If the ship is traveling at 33 knots, which is 17 meters per second, which is a standard speed for a battleship, how far in front of the ship do you need to aim? Assume there is no air resistance, because we live in a perfect world. So the first question is, what is the concept? Well, we really only have one now. It's kinematic equations. Now, the first thing we do once we get that settled is we draw a figure. So here's the ocean. And I have a ship out here. I have a bluff or a cliff. It's supposed to be vertical there. And we were given that the cliff stands 55.3 meters above sea level and that the ship is 1.575 kilometers or 1,575 meters away from where the cannon is. So I have my cannon here at an angle of 35 degrees above horizon, and I am looking for the initial speed. Now, when I fire this cannon, that cannonball is going to come out, and as soon as it comes out, it's going to immediately start to drop. And, well, that arc wouldn't have hit it, so let's go a little faster. So it's going to do something like that, and we want it to hit. So we've got a picture there. It's always good to have that picture to put in what you know and figure out in your head what's going on. Now, I want to list the knowns. There's one known that I did not put on my figure that I should have. It wasn't given in the problem, but we know that the acceleration in the vertical direction is minus g or minus 9.80 meters per second squared. Now, I used AY there, and of course, to use AY, I must define my x and y directions. That's an absolute necessity. Now, deciding what I know and what I don't know, I need to decide my reference points. Where do I want x to start measuring from? Where do I want y to start measuring from? Well, life is easiest if I choose this point. So that means I'm starting at x0 equals 0 and y0 is equal to 55.3 meters. And then I'm going to end at x final equals 1575 meters and y final equals 0. Oh, those weren't hard. Then we have the initial speeds. For the initial speeds, I need to take this V0 at 35 degrees and break it into components. So I'm going to have one component goes like that. That's going to be Vx0 because it's parallel to the x-axis. One component like that, that's Vy0 because it's parallel to the y-axis. And the hypotenuse is V0. It's the hypotenuse because it's opposite to the right angle. Now remember our trig functions. Sine theta is equal to opposite over hypotenuse. So if I look for the side that's opposite to this 35 degree angle, it's Vy0. Hypotenuse was V0. So if I solve that for Vy0, I have Vy0 is equal to V0 sine theta. Now if I do essentially the same work for cosine, cosine theta is adjacent over hypotenuse. So the adjacent side, the one that's participating in making my angle of 35 degrees, is Vx0 divided by the hypotenuse V0. So that gives me Vx0 is equal to V0 cosine theta. So Vx0 is V0 cosine theta. Vy0, well, these aren't actually, I'm going to put those down here. Let's go straight to theta is 35 degrees. We knew the acceleration in the y direction is equal to minus g. Acceleration in the x direction is 0. And we know the speed of the ship is 17.0 meters per second. And the first thing I'm looking for is V0. Now, breaking things into components, now I wrote the x0 is 0 above, and x final is 1575 meters. Y0 is 55.3 meters. I wrote above, and y final is 0. AX is 0. AY is minus g. So there's everything broken down. Now, if you look at this, I tell you what to do for the next step, but realistically, on the test, you have to figure this out. So how would you know, hey, let's solve the x direction for time? Time is the variable that ties the vertical and horizontal motions together. So that's why I think about time. Now, if we look at this, there's an unknown also there. So whether I am doing x or y, whether I'm doing x or y, I am going to have two unknowns. I'm going to have time as an unknown and V0 as an unknown. So if you think about it, it doesn't matter if I do the y direction first or the x direction first. And so then you say, well, why do you do the x first? Because the x has two zeros. It's going to be a simpler equation. So that's why I did the x first. So doing my x equation, because I have all the variables, I'm going to use the kinematic equation with all the variables. So there's my kinematic equation. Remember, I always put in my zeros right at the beginning. Why? Because it's a lot less to write. And so now I have x final is equal to Vx0t. Therefore, divide both sides by Vx0, and I have t is x final over Vx0. Now I'm going to plug that into the y direction equation. Well, the y direction equation is going to be using the same kinematic equation, just using it for y now. Substituting in, I have 1, 0. That 1, 0 is y final. So I have 0 equals y initial plus vy0. And then putting in what I just determined for t, x final over vx0 plus 1/2, my acceleration in the y direction is minus g. And then for t again, I substitute x final over vx0 quantity squared. And this, something that happens rarely, is simpler than it looks. 0 equals y0 plus vy0 x final over vx0 minus g x final squared over 2 vx0 squared. And you say, well, why is that simpler than it looks? Well, vy0 is v initial sine theta. Vx0 is v initial cosine theta. And so notice that my v0s actually cancel there. And sine theta over cosine theta is tangent theta. So I have I'm going to put the x final in front of the tangent theta. So far, so good, right? Well, let's move the gx final squared over 2vx 0 squared to the other side of the equal sign, which means I add it to both sides. So I did the addition by moving the minus sign to an equal sign and getting rid of the 0 equals. Now I want to solve this for vx0 or v0 ultimately. So let me substitute what vx0 is there. All right, so if I want to solve for the v0 squared, I'm going to have to multiply everything by v0 squared to get it in the numerator position. And then I'm going to have to divide everything by the stuff that was on the left side. And so I'm left with the relation that v0 squared is equal to g x final squared over 2 cosine squared theta. And then I had divided by, so here I have y0 plus x final tangent theta. And that's, yeah, I think I did that right. And assuming that I did all of my work right, that's 9.8 times 1575 squared divided by cosine of 35 degrees squared times 2. Doesn't make a difference in my answer. Times 55.3 plus 1575 tangent of 35. For some reason, that is not giving me the answer that I got before. Let me look at what I wrote more carefully, because I am quite certain that I indeed have the same relationship. Yeah, it's the same. Okay, what in the world did I typed in something wrong this time, I think, because I double checked my answer the first time. Gx squared all over 2 cosine squared Okay, I had a parenthesis in the wrong place. Whew. I'm sorry for that delay, but I do want to make sure that I get the numbers right. So if you square root that, now I know there is automatically a plus or minus when I do the square root, but I'm just looking for a magnitude, so I did not put the minus. So this is my launch speed. Now, of course, how many significant digits do I have in that launch speed? The answer is going to be 3. And so I'll put the 125 meters per second here, even though I have more digits that I'm going to use as I continue on. Now, question, is this a reasonable speed for the cannon? The speed of sound is about 340 meters per second, but typical artillery cannons have muzzle velocities of around 1,000 meters per second. Well, this is less than the speed of sound. It's actually a relatively slow cannon shot. You have a lot of range with cannons. Just check with Mythbusters if you don't believe. They had a very significant mistake when they were trying to test a cannon. They ended up hitting a house, hitting a car. It was funny. No one was injured, thankfully. Okay, so it turns out this is a slow speed, but it's certainly a possible speed. Now, return to my equation for time as a function of initial speed and calculate this time that the cannonball is in the air. So note my time is x final over vx0. So that's going to be 1575 meters divided by 125.07 meters per second cosine of 35 degrees. And that gives me a time in the air of 15.37 seconds. So again, three significance figures, 15.4 seconds it's in the air. And finally, how far do I have to lead the ship? The ship is moving, so I'm going to have for the ship, the distance the ship travels is equal to the speed of the ship multiplied by the time that cannonball is in the air. So that's going to be 17.0 meters per second multiplied by 15.37 seconds, or 261.4 meters. So 261 to correct significant digits. That's a fair distance to lead it, right? That's almost 3 football fields that you have to lead that ship to hit it. So this is a good kinematics problem. It's a different one than the ones we did in class, but it's still the same principles. So as you do more and more of these, you see, well, I'm doing the same thing over and over. I'm breaking into components. I'm applying kinematic equations. Most of the time, the same kinematic equation. The thought process is, how do I apply it? In what direction do I go? What do I solve for? Going to our second question, a person walks a vector of 1,305 meters at 30 degrees north of east, then 742 meters at 40 degrees north of west, and finally 2,840 meters at 20 degrees east of south. What is the displacement of this person? Solve it both graphically, and you will have to do this graphically, and analytically. Not necessarily this problem, but you'll have to show that you know how to do it. So choose a scale that will fit on one piece of paper and write that scale. Now, my scale is going to be 1,000 meters is equal to, I'm going to say it's 4 centimeters. You'll see when I show you the ruler. Well, here's the ruler. So I'm saying 1 centimeters from here to here. And so I'm saying 4 of those. So one, if I start here, I change because the ruler won't let me write away from it. So if I start there, that's 1, 2, 3. That distance there is going to be 1,000 meters. Okay, so given that, I'm going to draw these out. So starting at my origin, now notice I have, once I start drawing, I can't change the scale. So I change the scale now, and I think I'll be good. So I have X and Y indicated here with my north and south. And so putting one of those ticks at the origin, if I can do it, I am not the most gifted manipulator here. What you can't see is it doesn't move with your finger unless you're moving it enough. So the first vector is 1305. So 1305 is going to be, it's basically 250 meters for each one of these ticks. So if I go 5 ticks, that would be 1250. And then I have another 55, which is 1/5. So it's going to be, whoa, moved the wrong thing there. 1, 2, this is 3, 4, 5 and 1 tick. So there is my first. There's vector A. This angle here was 30.0 degrees. And now at the end of vector A, I put vector B. So vector B is at an angle of 40 degrees. I have to come back. Is an angle of 40 degrees north of west. Come on. 40 degrees north of west. So the first thing I need to do is flip this like this. And there I'm 40 degrees north of west. And put that on the tick. Change my color. And this is 742. 750 would have been exactly 3. So it's just under 3. Okay, probably a little more than that. Well, I'm going to live with it because that's as good as I can get. So there's my vector B. And that was 40 degrees. And then my vector C is going to be at 20 degrees east of south. So 20 degrees east of south. So there's vertical. So south would be straight down. Then I need to go 20 degrees east. So if I go 20 degrees east, that's going to tip it up to 70. So there's 20 degrees east of south. Let's get that on there. Nice. You can see why I have less faith in this. It's hard for me to get those lined up. And so let's choose orange. And now I'm going to go, oh boy, 2,840 is going to be 8, and 3 is 11. 11 would be 2,750. Then I've got to go another 0.4. So I think I need to raise this up. Okay, I'll do it. So I'm going to go 11.4. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, that should be 11.4. Kind of getting 1, 2, 3, 7, 8, 9, 10, 11.4. Yep. That's vector C. Putting vector signs on my vectors because I'm no idiot. And keep in mind this was measured. I will actually do it here just so I'm not in the way otherwise. 20 degrees east of south. So now that I have all of those, to get my answer, I need to draw the line that connects the starting and ending points. There we go. And that measures 1, 2, 3, 4, 5, 6, 7, 8.8. 8.8 centimeter scale at 45 degrees south of east. Now to convert that, I have 8.8 centimeters scale times 1,000 meters per 4 centimeters scale equals, so 8.8 divided by 4 is 2.2 times 1,000 is 2,200 meters. So my vector that I got from this is 2,200 meters at 45 degrees south of east. Now we're going to do it analytically. So doing it analytically, I need to take each one of these vectors separately. So I have my A vector was 30 degrees. Now I'm not worried about the length of the line. So there's my A vector. You want to Okay, so there I have the components. Remember, the components have to add up to the whole. So I have this here, A vector, this is AX, this is AY. There is my angle of 30 degrees, 30.0 degrees, I think. And so I have AX is the adjacent side. At this point, because we just went through the cosine and sine in the previous problem, we should be comfortable with the adjacent sides can be found using cosine. So AX is going to be a cosine of 30 degrees equals, and A had a length of 1305. So AX turns out to be 1130.163 meters. Now, notice I'm keeping ridiculous sig figs here. Notice I have an I hat there. That means in the x direction. That's what I hat means. Now for the y component, I'll have AY is equal to A sine of 30 degrees because AY is the side opposite 30. So that's 1305 meters sine of 30 degrees, which is 652.5 meters. It's 0, 0. So there we have A broken into components. Doing B, B was an angle of 742 at 40 degrees north of west. So 40 degrees north of west is like, yeah. Okay, so breaking this into components, I'm going to have this here is Bx. This here is By. Now notice Ax was going to the right, and my right was positive direction, so that was positive. Ay was going up, and I did not draw the arrow on that like I should have. And so that was also positive because up was positive. Here with B, my Bx is going to the left, so that's negative. So I'm going to throw a negative sign there right now. My By is up, so that's going to be positive. The angle I was given was right here. And so bx is the adjacent side, hence bx is equal to b cosine theta because it's adjacent, equals, what's it, 742? Yep, 742 at 40. 742 meters cosine of 40 degrees equals 568.405. And by is equal to b sine theta because it's opposite side, equals 742 meters sine of 40 degrees equals 476.948. So putting those in my table, I have minus, because of the direction, 568.405 and positive 476.948. Finally, my c vector. My c vector was like this. Oops, it's almost there. Come on, stop at 70. Got it. So my c vector was like this. So it had to go down. Wow, I really was not making good lines there. So this is the c vector. Here's cy. There's cx. So cx is to the right, that's positive. Cy is down, that's negative. So I can throw the negative sign in for cy right now. The angle that we were given was this angle here, 20.0 degrees. So now cx is the opposite side. So opposite side means it's going to deal with sine. So that's going to be 971.337 meters. Cy, that's the adjacent side, so that has to do with cosine. And that's going to give me 2668.73 meters. I did not give myself enough digits there. 727. Now, of course, I'm keeping way beyond significant digits. I just want to have digits so that they all match up. So putting in these numbers, 971.337 and negative 2668.727 meters. Now, to get my components, I add like ones. So the x direction, I'm adding all of those together. So 1130, I'm going to not say the decimal, minus 568 plus 971. That gives me 1533.095 in the I direction. And then adding up 652, 477, and negative 2669, I get minus 1539.28. Okay, so I've done part G in the bottom row of the table, add the column of numbers above it. Use Pythagorean theorem. Well, what I have right now is two components. 1533.095 meters. (1539.28 meters), and I want to find the hypotenuse. Right, this is a right triangle, and so I'm going to use the Pythagorean theorem, that is square root 1533.095 meters squared plus 1535.095 meters squared equals 2172.501 meters. So now that's my distance. How many sig figs do I have? Well, at best, I'm going to have 3. It's a little convoluted because of the way everything worked. But I had 4, 3, yeah. So I have 3. And so that's going to be rounding off to 3 significant figures, 2170 meters. And then for my angle, to avoid using an additional calculated value, I'm going to use tangent, so it relates the two numbers that I got directly before I used the Pythagorean theorem. So I have tangent of theta is equal to the opposite, 1539.28 meters, over the adjacent, 1533.095 meters. So I need theta, so I'm going to use inverse tangent on both sides, which gives me theta is equal to inverse tangent, otherwise known as arctangent. And that gives me theta is equal to 115 degrees. So I'll round that off to 3 as well. 45. That's 40. I'm just going to zoom in. 45.1 degrees. And then measured from where and to what direction? My adjacent side was the x direction, so that's my reference. So of x. And I went toward y, toward minus y, so it'd be minus y of x, or if you prefer, 45.1 degrees south of east. So now if we compare my values, I had 2,200, whoops, skipped. 2,200 at 45 degrees south of east from my drawing. I had 2,170 meters at 45.1 degrees south of east from my analytical method. My analytical method I have more faith in because I know I kept a lot of extra digits here. That's definitely right to 3 significant digits. Whereas the graphical one is not quite as accurate. Still pretty good. I mean, they agree. If yours don't come close to green, you made a mistake. They should be close. And in fact, I'm very proud of this work. It's pretty good given the ruler I had. So those are the skills that you will need to have from Chapter 3 for the exam. I hope this helps you get ready. Have a great night.